So, hello everyone, myself Naman Khetan. I am a senior undergraduate at IIT BHU Varanasi, India, and I have used the Altair Inspire 2024 to done the mass optimization of my retracting drone arm mechanism and its frame. So, first let's talk about the mechanism. So, the retracting drone arm mechanism is basically a slider crank mechanism having the crank, the forearm crank mount here, the connecting rod, and the slider. There will be propeller on the slider while there will be a motor on the crank, and this motor will cause the rotation, and there will be an inward and outward movement of this uh, slider, which will vary the distance between the propeller and the center of the drone. So you can see this motion in this way, and I intend to make this mechanism because currently there are a lot of innovations going on in drones to make them optimal for a variety of terrains, and I want to do the same by varying the drone arm length in my drone. So like it is considered usually that a drone having longer drone arms are quite stable, while those having shorter drone arms are quite agile. So I want my drone to switch between this stable and agile mode mid-flight, and thus I believe it can adjust to any terrain. So going forward towards the optimization part, I want to reduce mass in both frame and mechanism, but I have done their analysis and optimization separately in order to save computational cost. So first talk about the optimization in mechanism here. So I have make this design space in the forearm crank mount here and have applied the positional constraints here, the planar constraints here, and along with the motion analysis loads, I have also considered the thrust forces at the end of drone arms. After doing its maximum stiffness optimization, I am getting this type of structure as you can see here, and the factor of safety is of 6, and it is usually of the higher side, but for a drone I think it's actually good according to me, because usually in flight we can have additional loads in the form of aerodynamics and drags, and also this drone has so many moving parts. Going forward with the slider, so in the slider I have made the design space and applied the usual planar constraints and have considered the same loads here, the thrust loads and the motion analysis loads. And after doing its optimization, maximum stiffness optimization, I am able to get this type of structure here. And you can see here also the factor of safety is of 6. So yeah, it's actually good for me. And thus in the mechanism you can see that initially its weight was like 0.605 kg, but after doing their optimization I am able to get like 0.357 kg weight of the mechanism. In the frame there are like 4 holes on the upper plate through which the crank motor will be mounted, while on the lower plate there will be mounting of the drone landing gear. These are the sliding tracks on which the slider will do its to and fro motion, and thus these holes and tracks are my non-design spaces. And in the design space I have applied these planar constraints and weighted loads. So I have applied these weighted loads by considering the components I will be using actually in my drone. So there is actually like 20 Newton of force distributed in among the 4 holes in upper plate, and the 10 Newton of force in the same way on the lower plate. And after doing their maximum stiffness optimization, I am getting this type of structure. You can see that the von Mises stress are usually low, and it is only in the little bit higher and at the edges and the corners. Uh, and its factor of safety is also 6. So in the frame I am able to get a mass reduction from 1.201 kg to 0.718 kg. So in summary, I am able to get a mass reduction from 1.844 kg to 1.075 kg, which is actually 41.7% mass reduction with a factor of safety of 6. So this is what I intended to do with Altair Inspire, and it's a great learning for me. Hopefully you will like this also, and thank you for watching it.